Hi, I'm Zach with HKN, and today we're going to solve a circuit that has a capacitor in it. Now, a capacitor's behavior is governed by this equation here. If we have a capacitor with a voltage across it, the current through the capacitor is going to equal the capacitance times the time derivative of the voltage. So right away we can see from this that if there's a capacitor and the voltage is not changing across it, the current through it's going to equal 0. So then with a steady voltage, a capacitor acts as an open circuit. So when we solve this circuit that has a capacitor in it, we're going to end up with a differential equation. Today specifically we're going to be looking for the current through this resistor as a function of time. And we can see in this circuit that at time 0, there's a switch right here that opens up. We can assume that it's always been shut up until time 0. So that would imply that we have a steady value of voltage across this capacitor before time equals 0. So there's no current flowing in here until this switch opens. So we know from differential equations that your initial conditions are important. So we're going to solve for an initial condition. For this, we're actually going to solve for two initial conditions. One for this current and one for the voltage across here. So we'll use a current divider rule to solve for the initial value of this current. We can see that we have a current source that is split up into two resistive branches. And now our current divider rule says that the current through this branch is equal to the total current times the resistance of this branch over the resistance of the sum of the resistance of both of them. So the current through this branch is going to be equal to 4 amps times the resistance of this branch, which is 6, over the resistance of both of these branches, which is going to be 6 plus 3. Now this is going to equal 8 over 3 amps. So that is our initial value before time equals 0 of this current. Now we can also get from this an initial value for this voltage. There's no current flowing through here, so the voltage across this capacitor is the same as the voltage across this resistor. And since we know the current through that resistor, we're going to call values before time equals 0, 0 minus. So your voltage across your capacitor at time 0 minus is going to equal the current through this resistor times its resistance, and that's 8 over 3 times 2. (16 over 3 volts). So now we can set up a differential equation and solve it using these initial conditions. So we can see that at time equals 0, this switch opens. And without this switch here, this part of the circuit is separate. Nothing that happens over here affects this part of the circuit at all. It's its own circuit. So we're going to redraw this circuit just to, it's a little bit easier to work with, and then we'll solve the differential equation. Okay, so here is our circuit after the switch opens. Now, we can see that the current we're looking for is the opposite of the current flowing into the capacitor. So that gives us this relation. I naught is equal to negative IC. Now, we know that IC is equal to the change in voltage across the capacitor times the capacitance value. And we know that the current in this resistor, I naught, is equal to the capacitor voltage divided by the resistance. So, I naught, let's change the position of this negative sign real quick. We're going to multiply both sides by -1 and get that negative I naught is equal to IC. So, I naught is equal to VC over 2 ohms, and that's negative, and this is going to be equal to the capacitance value, which from this is 300 microfarads. We'll call that C for now. So, this is our differential equation. We can see that it's a separable differential equation, and so it can be solved by separating our variables and integrating both sides. And so we're going to do that here. Now, when you separate this into 2 sides, it's going to give us and when we integrate both these sides, we're going to integrate the side that involves t from 0 to t. And we're going to integrate this side from our initial value of VC to our value of VC at time t. Now this is going to result in we can take the exponential of both of these sides. That will result in and we know a definite value for VC at time equals 0. We figured our initial conditions. VC at time equals 0 is 16 over 3 volts. So we can multiply both sides by that, and then we'll get VC T is equal to 16 over 3 volts times E to the negative T over 2 times our capacitance. And our capacitance is 300 microfarads, so this is going to be equal to 600 microfarads, which is 600 times 10 to the negative 6. And that is in seconds. That's going to be in seconds so that your time and divided by it cancels out to a non-unit number. All right, so now we have a function that tells us what the value of the voltage across the capacitor is at any time after t equals 0. Now our problem initially asked for the current through this capacitor as a function of time, and we can see that the current through here is going to be simply the voltage across the capacitor divided by that resistance value. So I naught of t is equal to Vc of t divided by 2, and that is going to equal 16 over 6 amps times e to the negative t over 600 microseconds. And that is our answer.